So, in the topic of energy cycles, the Born Haber cycle is the cycle that we choose when we are dealing with ionic compounds rather than the Hess cycle which we used for covalent substances, but not only. And in particular, it's when we're dealing with lattice energy of ionic compounds. So if we start with the basic construction of a Born Haber cycle, we can start with the elements in their standard states, that's their states under standard conditions, 298 Kelvin, 1 atmosphere pressure, and we can take those elements and turn them into our ionic compound, and if that's the case, we're looking at the interchange of formation. But in a Born Haber cycle, we can go, at least theoretically, through another route where we take those elements and turn them into gaseous atoms. And then once we've got the gaseous atoms, we can then ionize those, forming gaseous ions. And once we have the gaseous ions, and theoretically, we could take them and make the ionic compound. So the energy changes involved at each stage. To go from the elements to gaseous atoms, we're talking about interchange of atomization. To go from gaseous atoms to ions, we're either talking about ionization energies if we're making positive ions, or electron affinity if we're making negative ions. And when we take the gaseous ions and put them together to make the ionic compound, the energy change we're talking about is the lattice energy. So obviously, in order to do that, we need to know what these definitions mean and be able to write down the reactions or the reaction equations for each one. So let's make sure that we do. The enthalpy change of formation is when 1 mole of a compound is formed from its elements in their normal states under standard conditions, which we will call their standard states. If you need a reminder of what the standard states are, look at the Show Me on the Hess cycle. So we could take an example here. For sodium chloride, we would take sodium as a solid, and we would take half a mole of chlorine gas, because chlorine is diatomic, and we would be forming 1 mole of sodium chloride. So that's enthalpy change of formation. So let's look at enthalpy change of atomization, and this is when 1 mole of gaseous atoms is formed from the elements in their standard states. And an example of an equation here would be when we take half a mole of chlorine gas and form 1 mole gaseous chlorine atoms. So our next definition is the ionization energy. And we might have more than one of these depending on the ion we're forming. So if we look at the definition for the first ionization energy, this is the energy change when we remove 1 mole of electrons from 1 mole of gaseous atoms. And of course these gaseous atoms would have been formed in the atomization stage of the cycle. And of course we can have a second ionization energy where we've removed, it's the energy change to remove 1 mole of electrons from 1 mole of gaseous 1 plus atoms. So we've already, gaseous 1 plus ions. So we've already removed the first mole of electrons, if you like. And an example where this may come up in a cycle is when we actually need to form a 2 plus ion. So notice in this case we would have to do both energy changes. In a similar way, we would use electron affinity, which is when we're forming negative ions. So in this case, the first electron affinity, we're forming 1 mole of gaseous 1 minus ions from gaseous atoms. So here we would have formed the gaseous atoms again in the atomization stage. We can also have further electron affinity, and similar to the ionization energy, we're forming 1 mole of the next charge up from the previous charge. So 2 minus ions from 1 minus ions. So an example where this might come up would be we'd already formed 1 O minus, and then we want to form O2 minus in our cycle. And the last one is the lattice energy, and this is the energy change when 1 mole of an ionic compound is formed from its gaseous ions. So an example here would be gaseous 1 plus sodium ions, gaseous 1 minus chloride ions coming together to form solid, 1 mole of solid sodium chloride. Okay, now we have all the definitions. Let's do an example and find the lattice energy for sodium chloride. So if we look back at the general structure where we have elements going to atoms, going to ions, and then coming around to ionic compound, we can do this for sodium chloride. So we start here with the elements, and then we could do delta HF to form 1 mole of sodium chloride, or we can go this way around and form gaseous 1 mole of gaseous sodium atoms and 1 mole of gaseous chloride ions. And of course there we're talking about atomization of sodium and atomization of chlorine. And then of course in the next step we're forming gaseous ions. So here we're doing the first ionization energy of sodium and the first electron affinity of chlorine, and then our lattice energy would be going from here to here. So as in his cycle, we can look up the data. The enthalpy change of atomization for sodium is plus 109 kilojoules per mole, and we'll assume these are the units for all of the energy changes. And atomization energy for chlorine is 121. The first ionization energy for sodium is 500 kilojoules per mole, and the first electron affinity for chlorine is minus 370. And again, if we look up delta HF for sodium chloride, we find it is minus 411 kilojoules per mole. Now, since we're trying to find a lattice energy, which starts here, we can go direct, but that's what we're trying to find. So we can go around the energy cycle this way to use the energy changes that we know. So if we put the numbers in, we're going against the arrow at the top here, which basically means we have to change the sign. So we do minus 500 minus 370. In the next step, we're also going against the arrow. So we do minus 109 minus 121. And in this third step, delta HF, we're going with the arrow. So we go plus minus 411. And when you press all the numbers in the calculator and work out the maths, we find the lattice energy is minus 771 kilojoules per mole for sodium chloride. Try the maths for yourself. But we can be asked not just to find a lattice energy, but maybe find the enthalpy change of formation if we're given a lattice energy. So in this case for calcium oxide, the lattice energy we might be given is minus 3,401 kilojoules per mole. So let's construct our cycle. So we have our elements that can be used to form our ionic compound, and this is delta HF, which is what we're actually looking for here. So then we can do our first step where we atomize the calcium, form gaseous calcium atoms, and we atomize the oxygen, form gaseous or 1 mole of gaseous oxygen atoms. And then we have our second step where we take those gaseous atoms and ionize them. So putting in those energy changes, we see that this time we have to do the first and second ionization energy of calcium and the first and second electron affinity of oxygen. And the final energy change in our cycle is the lattice energy, when we take the gaseous ions and turn them into our ionic compound. So let's put in some numbers, starting with the lattice energy that we know. If we look up atomization of calcium, we find it's plus 177 kilojoules per mole. Atomization of oxygen is plus 249. Ionization energies of calcium, the first one is 590 kilojoules per mole, and the second one is 1100, and that is positive also. With the electron affinity of oxygen, the first one is minus 141 kilojoules per mole, and the second one is positive, so it's endothermic, 790 kilojoules per mole. Now we want to go from here to here to find delta HF, and this is the same as going round the Born Haber cycle this way. So we start putting the numbers in. We're going with the arrow in the first step, the atomization. So we do 177 plus 249. And then in the second step, we're also going with the arrow, so all the signs stay the same. So it's plus minus 141 plus 790 for electron affinities of oxygen, plus 590 and plus 1100 for the ionization of calcium. And then we come round this right hand side and we do the lattice energy, so it's plus minus 3401. So putting all those numbers into the calculator and working out the maths, we find that the enthalpy change of formation of calcium oxide is minus 636 kilojoules per mole. Try it out for yourself and find some alternative examples and see if you can do the same.